Okay, so this is going to be the Quantum Club core content series video on quantum gates. We're going to be talking about quantum gates today. And these quantum gates are going to be dealing with one qubit systems. So this is going to be a nice introduction to the idea of quantum gates acting on quantum states. We're going to focus on one qubit systems that's nice and simple. The dimensions are low, and obviously this information we can, or there will be a second video made on this channel by Max later. This will be out after this video, which will deal with quantum gates in a higher qubit or higher dimensions and systems of more qubits with entanglement, tensor products, and things like that. So, of course, we have our quantum state. It's called psi, alpha, and beta right here. And this is the vector notation. Obviously, if you watch Anthony's video, you're familiar with this. So where alpha and beta are going to be complex numbers, of course. So these states are complex. And we just want some easy example, the off state right here, 1, 0. So these are actually what we call our state vectors, right? So this right here is going to be a state, or let's write it here. Psi right here is a state vector, okay? So what's interesting about this is that we can actually write, so the actual quantum state is going to be this outer product right here. So if you watch Anthony's video, again, you'll be familiar with this operation, the outer product. So we have alpha, beta, and we have alpha bar, beta bar here. And this outer product will give us our resultant state, alpha alpha bar, alpha beta bar, beta alpha bar, beta beta bar, right? So this is going to be our resultant state matrix, okay? And this is what we're actually referring to when we say quantum state. This right here is a quantum state. But this operation is just implied when we talk about states, so we can just keep our notation right here as state vector, and we're just going to call this a state. We don't have to worry about this word vector, okay? So now that we have that out the way, one interesting property of these quantum states is that their norm squared is 1. So the norm of a complex state is just going to be this operation, right? Inner product with itself. If you watch Anthony's video, you'll be familiar with the inner product operation, but we just have the complex conjugate right here, and then alpha beta. And this, if you do, this is a scalar, we get alpha alpha bar plus beta beta bar, and this will equal 1. Now, if you're familiar with complex operations, you would notice that this is going to be the norm squared actually of this complex number alpha. So this would be the norm squared of this complex number beta, and these would equal 1, okay? So this inner product is always going to equal 1. That is a fact. And this is a squared, right? Because if this wasn't squared, this would be a square root here. We actually deal with norm squareds in quantum computation. That's just a conventional thing because we don't want to have square roots in all of our computation. It would be much easier to just deal with the square root of it, and it doesn't actually change any fundamental properties because 1 squared is 1. So, anyways, if you would notice, one of the interesting things about these being in the complex dimensions is we actually have a bunch of degrees of freedom, right? So if you notice, if we just go to like if we so first off, let me just write this state. If alpha is a plus bi and beta is c plus di, right? We have 4 dimensions we can work with. We have our 2 Cartesian dimensions, and we also have 2 complex dimensions. So one of those complex dimensions is going to be magnitude, obviously. So within the bounds of 1, you can also have this. So this is true for a pure state, right? Generally speaking, so generally, actually, I don't know if I should say that, but so sometimes we can work with states which have a magnitude of less than 1, which is why our representation of them is going to be 3-dimensional, not hollow, or fully 3-dimensional, solid 3-dimensional, not hollow, because there is information stored on the inside of the circle, but that is not the states that we're going to be working with in this video, and especially not on Qiskit when we're programming quantum states. We're going to be mostly focused on what we call pure states, and pure states are going to have magnitude 1, so or norm 1. Sorry. So if this is a complex dimension, or this is a complex plane, right? We have imaginary here and real here. We would just take this, draw some circle. Now, if we'd imagine that this is our unit circle right here, um, this means that all this magnitude around the circle would be 1, okay? So you could have some complex vector here, and you could rotate this complex number, applying some linear transformation. You could rotate here, scalar, linear, scalar product. Why did I just say scalar product? What the hell am I talking about? Apply some transformation, you're going to get rotation around this complex unit circle, right? That's one of our degrees of freedom when it comes to these complex numbers. But the problem is that that would leave us with 4 degrees of freedom. You can't represent 4 degrees of freedom easily on a graph. So what the key lies in the fact that these are actually these state vectors. Okay, let me back up a little bit. So we this rotation would actually just be a complex phase, right? So if you're familiar with electrodynamics, you've heard a little bit about that, then you'll be familiar with the concept of a phase angle and a wave, which would you'd have some wave, right? And I'm really bad at drawing waves, y'all, so just bear with me. You'd shifted by a phase angle, now it's here, whatever. This is not what we're talking about. We're talking about, I mean, maybe it loosely relates in some mathematical connection, but generally what we're speaking about is some phase e to the I theta, okay? So if you recognize, or if you know Euler's identity, you recognize this as a complex number with magnitude 1 and some angle theta, right? So we can write, there's going to be magnitude 1, right? Because we obviously can't extend it outside of the circle. So there's always going to be magnitude 1. We don't even have to consider the magnitude. And we're just left with the phase angle. So this is what we call a phase. And these are really important because if you multiply some vector by e to the it'd be e to the I theta scalar multiplied by some arbitrary quantum state, right? So if we want to write e to the I theta using Euler's identity, of course, cosine theta plus I sine theta. So imagine if we had some phase e to the I pi. Looking at this expression, you would know that this is just -1. So if we wanted to apply this phase to, let's say, our off state, right, just as a trivial example, say e to the I pi on off is going to be our resultant vector is going to be -1, 0, right? So interestingly, let's see what happens when we actually turn this into a matrix, right? Because we now we have this -1 here. What do we do with this -1? We're not totally sure. It's not very familiar. It's I don't know how to represent a bit of computer information when it comes to negative numbers, right? So, and this is just our off bit with a negative number on it. So let's multiply this out to our actual state matrix and see what we get. So, and let's just represent this as an arbitrary. So let's say alpha equals e to the I pi, or not e to the I pi. Let's just call it e to the I theta. So any phase e to the I theta. Okay. So now, if we write this outer product, so we have alpha times some arbitrary state psi. Let's call this new state phi, right? This is phi is just going to be this state psi with this scalar e to the I theta applied to it. So now we want to find the state matrix of phi. So we're going to take the outer product of phi with itself. And if you extrapolate that to this, or if you substitute back in, you get alpha psi times alpha bar psi, right? Because we have to apply this complex conjugate, which is going to apply to both the scalar and the vector. And since we know that the magnitude of alpha e to the I theta is always 1, and if you're familiar with complex numbers, you'll notice that this, if you're familiar with linear algebra, you know obviously these scalars can move wherever they want. And you'll notice that alpha alpha bar is precisely 1 for any scalar e to the I theta for any phase, right? So we can pull these out to the side, and this would be 1 times the original outer product, which is exactly what we would have gotten without the scalar right here, right? So this means that we can actually project out, or you call it projecting out. Maybe that's not precise verbiage, but you can project. Basically, think of it as projecting out this dimension right here. So now we only have 3 degrees of freedom to work with. Okay, and that's going to lead us to the block sphere. Okay, so this is our block sphere right here. So one interesting thing you'll notice about this block sphere is that, well, first of all, we have our 3 coordinates right here. So we have one coordinate, which is the z coordinate, z-axis right here. We have off and on. We have the x-axis plus and minus, and the y-axis plus I minus I, right? So so this creation is the result of a higher level mathematical transformation called the hot fibration. It's very beautiful, very satisfying. It's way beyond the scope of what we're talking about here, but if you want to learn more about it, I'm sure there's a 3 Blue 1 Brown video or something that you can check out. Basically, an interesting result of the hot fibration is that you're going to be left with these anti-parallel orthogonal bases, right? So that might have been a total bunch of jargon to you, but if you watch Anthony's video, you're familiar with the concept of bases in linear algebra. You'll know that off and on would be our standard bases, 0, 1, 0, and 0, 1 for just an XY plane, if you want to think about it like that. But so that means that off and on in a normal coordinate plane would actually be orthogonal to each other. But in this case, they are directly opposite of each other. So that's just one interesting result. And so this isn't just a normal coordinate plane. Like you wouldn't just this isn't just, oh, this extends to, these are all the points between 0 and 1, 0 and 1, 0 and 1 on each of their respective axes. Like there's actually a lot of information encoded in here. And when we talk about observables in a later video, we will touch on that as well. So back to the plot. Let me go ahead and grab my little example block sphere. So now, obviously, we can represent quantum states, or these quantum states we were just talking about, as vectors on the sphere, right? So since they all have norm 1, they would all be extending to the edge of the sphere. We can kind of just draw them everywhere as we please. Now, the how do we accomplish this, right? So we have some vector here, we want to move it here, and then we want to move it here, and we want to move it here. How do we do that? Well, that's going to be a linear transformation. And what are linear transformations in linear algebra? Of course, they are matrices. Okay, so they're matrices. So for some matrix A, B, C, D, the linear transformation would be A on the side. Okay, and we have to write this this way, right? Because of course, when you match dimensions with linear algebra with multiplication, when you're multiplying it 2 by 2 by 2 by 1, this has to be how it goes. You can't write it this, it would never be um psi A. This is never possible, okay? Unless you would have to do psi outer product with psi and then A. But that's kind of just it's not super important. You just have to know that you always have to apply it on the left for the linear algebra sake. So you actually, like, if you want to apply A and then B and then C, you would kind of step, step, step. Anyways, so of course, we have to maintain throughout when we do this linear transformation. One interesting thing that we have to maintain is we have to make sure that the norm stays 1, right? So we have to maintain the information stored in the fact that it is on the edge of the block sphere. We can't have some original state right here and then apply linear transformation. It's all the way out here. This is bad. This is not possible. We don't want that, right? So that, and the secret to that lies in the inner product, right? So if we have psi, the inner product of psi is its norm squared, which is going to be 1, right? So we have to maintain this property. So now if you're thinking ahead, then you might remember this computation we did with the phase, okay? And projecting out the phase right here. It was right here. Scroll past it. So we're going to do a similar process right here. So let's call some gate U, okay? We're calling it U because it's a unitary, and you'll find out what it means to be a unitary in just a second. So U is just some matrix, okay? Any matrix. It can be complex, so we're just going to call it in the four-dimensional complex plane because it's a 2 by 2 matrix. I'm pretty sure that's correct notation. Maybe it's not. Maybe I just wrote something stupid. If I wrote something stupid, right, tell me in the comments. I'm always trying to learn. But anyways, some matrix U. We're going to apply this matrix U on psi, okay? We're going to see what property we have to satisfy to make sure that the normal size stays 1. So U on psi, let's call this phi again. Now, if we want to take the inner product of phi, that would be that expression. But so when you apply this transformation, then we need the conjugate transpose of this matrix and this vector right here. So now, if we want to rewrite this using what we had before, we can have the complex or the conjugate transpose of psi, the conjugate transpose of U. So the conjugate transpose of our matrix, we're always going to write as with this little symbol right here. We'll just write a star. It's actually more standard, I think, to use the dagger symbol because that's like, for example, in Qiskit, when you're using the conjugate transpose of a gate, right? Like for example, the S gate, SDG. So this DG is going to mean back dagger. So maybe the dagger is more standard, but we're going to use the star because that's how I learned it. So now we have this expression, which is just going to be the conjugate transpose of this right here, and then we're going to write our original one. Now, if we want to make sure this has to equal 1, right? So we already know that this equals 1. This multiplied with, or this inner product with this equals 1. So that means that this in here must be the identity matrix, right? It must be the identity matrix. Otherwise, the norm squared would not still be 1, and this property wouldn't be maintained. So there we go. That's what it means to be a unitary. U star U equals U star equals the identity matrix. This is important, okay? This is a unitary property, okay? So any unitary gate which operates on a quantum state and maintains the quantum information in it is going to be a unitary, or obviously because it's called a unitary gate, but this is going to be the property that it satisfies. So this gives it the ability to transform quantum states without collapsing them. Excuse my handwriting, it's early. Right. So this is important. Okay. So now let's go to some examples of unitary gates. So now let's just transition and go all the way down here. So common unitary gates. So this is checkpoint one right here. We've kind of gotten all the lore of gates. So now we're looking at some examples. If you have any questions, please leave them in the comments. Please let us know. We're always trying to help you guys. And obviously, if you're not watching this on YouTube and you're just in the Quantum Club, you can just ask us on Wednesdays. So anyways, common unitary gates. Let's start with the Pauli matrices, okay? Pauli matrices. So these are important because Pauli matrices are also observables. There are unitaries and observables, but you'll figure out what that means in a later video. For now, we're worried about the transformations. So the two most common Pauli matrices we're going to be using. So, okay, it's more standard to write them in sigma notation, sigma x, sigma y, and sigma z. But I don't like this notation. The notation I learned it in was just capital X, capital Y, and capital Z. Okay, this is what I'm going to use for this video. But just know that if you're talking to any quantum physicist that's in grad school, anything like that, they're going to use this because this is more standard. But I like these ones because it's just simpler to write. So, anyways, X, Y, and Z. So the two most common out of these are X and Z. X is this matrix right here, 0, 1, 1, 0. And Z equals this matrix right here, 1, 0, 0, minus 1. Okay? Now, if you want to pause the video and try to figure out what these matrices do on your own, you can try to imagine X on off or Z on off, or Z on. Okay, so let's use these two examples since Z doesn't actually do anything to the off state. So that would look like 0, 1, 1, 0 times 1, 0, and this would look like right here, and this would look like 1, 0, 0, minus 1 on this one right here. Okay, so if you want to pause the video and do this math in your head or do it on a paper, you would figure out yourself, but I'm going to do it real quick. This transformation is going to give you 0, 1, and this transformation right here is going to give you 0, minus 1, okay? So this, you can see that X is the bit flip operator, and Z adds a phase to this one right here. And Z would just multiply whatever's in this spot by a negative sign. So there's a third gate, Y, of course. The Y gate is going to be 0 minus I, 0. Now this is a more interesting gate. It's harder to tell whether or not it's unitary. You can check it yourself if you want. But this gate is less commonly used because it's a more nichely applicable. You know what I mean? Like it's very useful, but only in specific scenarios. And X and Z are a lot more generally usable, and they're a lot easier to understand what they do. So now if we continue on, those are our first three common unitaries that we want to talk about. But now we're going to talk about other unitaries that you'll see a lot. The first one is the Hadamard gate. Now the Hadamard gate has the interesting property that this is our superposition gate. Okay, so if you want to take a state and you want to put it in superposition, the easiest way to go about it, this is going to be our superposition state. So if we can apply this gate onto onto our off state, right? So this expression is just H off right here. Then you would get 1 over root 2, 1, 1. Okay? And this, of course, not of course, you actually haven't heard this before. This is our plus state. Okay? So we go back to, if you go back in the video to where I pulled up the block sphere, you'll notice that this is the positive x axis vector. Okay? So this is the positive basis of x, and there's also minus. So if you were to apply this h1 equals this matrix applied to 0, 1, I'm not rewriting all that, and that is going to get 1 over root 2, 1 minus 1. Okay? So, and this is going to be minus. Okay? So this would be the minus x version of the basis. And these are in superposition. And you could rewrite this as 1 over root 2. This is a normalization factor, by the way. This 1 over root 2 is a normalization factor because you'll notice if you did the norm squared of this, but if you multiply by 1 over root 2, that's going to cancel out inside the square root. It's going to make it 1. And you could rewrite this plus state right here as 1 over root 2 off plus on, right? With the known coefficients being 1 and 1 here. And this is exactly how you write superpositions. Generally, when you're talking about quantum states, you could write um, some normalization factor times alpha times on plus beta times off if the coefficients were unknown, right? So the normalization factor stays there because you still want to make sure that when everything squares and adds to 1, you get 1 over, like if this was psi, you get 1 over norm psi. This would be the normalization factor, and then, of course. So anyways, some other common unitaries, including Hadamard gate, are going to be, we have our H gate, we have our S gate, and this is going to be 1, 0, 0, I. And then we have our T gate, 1, 0, 0, e to the I pi over 4. And the T gate kind of gives it away. I was going to ask you guys to figure this out yourselves, but something interesting about you, let's look at these three matrices, right? What do you notice about all these matrices? If you were paying attention earlier, and maybe you're still paying attention, you didn't make this connection, and that's perfectly fine. These are all phases, okay? These are all phases. So this would be e to the I pi over 4, obviously, is very explicit, but this one would be e to the I pi over 2 right here, because if you're using Euler's identity, that would just give you I, and this would be e to the I pi, as we used in our example at the beginning of the video right here. So the generalized version of this gate is I'm not actually sure what the denote like what they denote it as, like what the letter associated with this, but the generalized version of this gate is going to be 1, 0, 0, e to the I theta. Okay, and these are just commonly used angles. These are very applicable. They're very useful. And so they get their own little representation right here. But this is the generalized version. This is the parents matrix. And then of course you have some rotation gates too. So Rx of theta would be you can apply rotations to states, which would put them not on the axes, but is somewhere inside the block sphere. These ones you use them less, and they would give you more complex probabilities, and not complex in the sense of like complex numbers, but just more interesting probabilities because they would put you instead of on one of like z and x will keep you on these axes here, and h will keep you on these axes here, but the rotation gates and the s and t and they will put you somewhere on the inside of the sphere. That's not just on one of the axes. So yeah, these Rx, Ry, and Rz are something that you will see in Qiskit. There are, like I've used them in Qiskit in my own work, trying to create examples and things like that. These are important to keep in mind as well. Okay, so these are some common unitaries that you guys are going to want to keep in mind here. Okay, so these are the gates that we're going to be using to transform our quantum states. And that's about all I have for you. So hopefully this video was instructive. Hopefully you guys found this video useful. Hopefully you're going to be able to take something out of this and apply it to your time using Qiskit and your future endeavors in quantum. Um, Go ahead and leave some feedback if you guys have any. I'll be happy to take it and apply it to the future videos we make on this channel. And I will catch you guys later. Peace.